how can a few hours literally cost you 23 years of your life? Okay, let's dive into this. Do you remember that scene in the movie Interstellar where the astronauts visit a planet near a black hole, and after just a couple of hours on the surface, they get back to their ship, only to find that over 23 years have passed for the crewmate they left behind? It's a totally mind-bending scenario, but it isn't just Hollywood magic. It's actually deeply rooted in the profound reality of black holes, where extreme gravity severely, almost unbelievably, slows down the passage of time.
In this explainer, we're demystifying black holes, tracking them from their explosive birth all the way to their ultimate, kind of baffling death. We're going to completely change how you look at space, time, and the very fabric of reality.
All right, Section 1, Birth of a Cosmic Monster.
So before a black hole can even exist, it starts as a dying star fighting a billions of years-long cosmic battle against its own weight. Right now, our sun is burning through roughly 500 to 600 million tons of hydrogen fuel every single second. That's a lot of energy pushing outward, right? And it perfectly balances the crushing inward pull of the star's own massive gravity. But eventually, that fuel runs out. When it does, gravity wins the battle. It takes complete control and violently collapses the star's core right in on itself.
And that brings us to a magic number, 20. This illustrates the threshold perfectly. If a collapsing star is on the smaller side, it might just become a dense white dwarf or a neutron star. But if that dying star is more than 20 times the mass of our sun, well, literally no force in the known universe, not even the fundamental rigidity of matter itself, can stop it from completely collapsing into a black hole.
Moving right along to Section 2, Warping Space and Time.
To really wrap our heads around what that collapsed star has just become, we kind of have to toss our everyday intuition out the window. For a long time, thanks to Isaac Newton, we just saw gravity as this mysterious pulling force acting across distances. But Albert Einstein came along and proved that gravity isn't a pulling force at all. It's actually the extreme curvature of space-time. Think about it like this. If you drop an apple, it's not actually being pulled down. The apple is just following its natural straight path, and the curved ground of space-time is essentially accelerating up to meet it. A black hole is simply where this curvature gets absolutely unfathomably extreme.
Now, what's really wild is how long it took to actually prove these theoretical monsters existed. Einstein published his theory of relativity in 1915, and the very next year, Carl Schwarzschild mathematically found black holes hiding in those equations. But physicists debated if they were even real for decades. In the 1970s, Stephen Hawking and Kip Thorne even made a famous, friendly bet over a mysterious energy source called Cygnus X1. Hawking bet it wasn't a black hole, and he actually lost. Today, we've gone way beyond just math. As of 2019, we have literal photographs of the supermassive black hole in galaxy M87.
Okay, Section 3, Anatomy of the Abyss.
So what exactly makes up the physical structure of these things? First off, let's categorize them. They generally fall into three main types. Stellar black holes are the remnants of those collapsed stars we talked about, usually 10 to 20 times the mass of our sun, scattered all over the Milky Way. Intermediate ones, well, they're a bit of a mystery, sort of bridging the size gap, and we aren't totally sure they exist. But the true giants? The supermassive black holes. These have the mass of millions, sometimes billions of suns. They literally act as gravitational anchors at the center of almost every large galaxy, including our own Milky Way, which houses one called Sagittarius A star.
Now, the absolutely crucial point in the anatomy of any black hole is the event horizon. This is it, the ultimate point of no return. The curvature of space here is so insanely severe that to escape it, you would have to travel faster than the speed of light, which, as we know, is impossible. To put that density into perspective for you, if our sun were magically squished down to a radius of just 3 kilometers, it would form an event horizon and become a black hole. To make it easier to conceptualize exactly why light can't escape, physicists use something called the river model. Imagine space itself is a river flowing toward a massive waterfall. Far away, the current is nice and slow. But right at the edge, the event horizon, the literal river of space is plunging inward at exactly the speed of light. If a beam of light is a fish trying to swim upstream, well, right at that horizon, it's swimming at the speed of light against a current moving at the speed of light. It's just frozen in place, completely trapped.
And once you cross that event horizon, you are inexorably dragged toward the singularity. This is the very core. It is where all the mass of that collapsed star has been crushed down into an infinitely small, infinitely dense point. It's the place where all of our known laws of physics just break. They completely stop making sense. And here is where things get truly, truly weird. Because space and time become so intensely warped inside a black hole, they effectively swap roles. Think about that for a second. The singularity isn't just a physical place you're falling toward, it actually becomes a moment in your future. You cannot avoid falling into the singularity any more than you can avoid tomorrow arriving. Your fate is literally sealed in time itself.
Which brings us to Section 4, Feeding the Beast.
Now, since black holes emit absolutely zero light from within their event horizons, you're probably wondering, how on earth do we actually see them feeding? Well, we can't see the hole itself, but we sure can see the glowing dust and gas swirling violently around it before it vanishes. Think of it like a toilet drain in a pitch-black room but filled with glow-in-the-dark water. You can't see the drain, but when you flush, you see that glowing water form this violent, superheated whirlpool, which we call an accretion disk, right before it gets sucked into the void.
What's really wild is that a feeding supermassive black hole can look completely different to our telescopes, just based on our viewing angle. If we're looking top-down at that blindingly bright accretion disk, we call it a quasar. If we look at it from the side and see these giant, powerful jets of matter blasting outward, we call it a radio galaxy. And if one of those high-speed relativistic jets happens to be pointing directly down the barrel at Earth, vastly magnifying its brightness, we call it a blazar. But get this, it is all the exact same monster, just viewed from different angles.
But what if you were the one feeding the beast? Say you personally fell into a smaller stellar mass black hole. Well, you wouldn't survive long enough to see the singularity, because you'd be so close to the center, the gravity pulling on your feet would be vastly, vastly stronger than the gravity pulling on your head. You would undergo a gruesome process that scientists, no joke, actually call spaghettification. You'd literally be stretched into a thin string of atoms and torn apart. So, thankfully you're safely watching this explainer instead.
Finally, let's look at Section 5, the ultimate death. Because, despite their totally fearsome reputation, black holes aren't actually immortal. Back in the 1970s, Stephen Hawking made a monumental discovery. He realized that the vacuum of space isn't actually empty, it is bubbling with quantum fluctuations that create pairs of particles and antiparticles. If this happens right on the razor's edge of the event horizon, one particle can fall in, but the other can escape. This means the black hole is slowly, steadily leaking energy. It emits this incredibly faint glow known as Hawking radiation, and as it radiates, it slowly loses mass, meaning over unimaginably long eons of time, black holes will eventually just evaporate into nothing.
But this evaporation creates what is arguably the greatest crisis in modern theoretical physics, the information paradox. See, the fundamental laws of quantum mechanics say that information in the universe can never be truly destroyed. Even if you burn a book, the information of the text still technically exists in the smoke and ashes. It's just scrambled up. But Hawking's original math showed that Hawking radiation carries zero information about what originally fell into the black hole. So, if the black hole vanishes entirely, where on earth did the information go?
And that leaves us to a fascinating, totally unresolved question to leave you with. Recent papers suggest that perhaps the information isn't lost at all. If a superbeing in the far future could somehow collect every single bit of Hawking radiation over trillions of years and feed it into a giant quantum computer, they might actually be able to reconstruct everything that ever fell in. So, as we wrap up this explainer, I want you to think about this. When a black hole finally dies, does it truly erase its victims from existence forever, or is the universe just keeping the ultimate, highly encrypted secret backup?